Hello everyone, and thanks for watching Edupedia World videos. In this video, we begin with a case which ideally would have been the very first case we did in quantum mechanics, the free particle without any potential. But in quantum mechanics, this problem tends to be somewhat tricky, so we did it after we did the infinite square well and the harmonic oscillator, so that before trying to attempt this problem, we got a little bit of understanding how you're essentially supposed to solve a Schrodinger equation or solve a quantum mechanical problem. Now, in the free particle, everywhere we would have the same formula because basically V is equal to 0 everywhere. And this is different from the infinite square well, where V was 0 in a particular region, but outside that V was infinity. So the free particle, under no influences of any forces whatsoever, will have the potential energy being 0 everywhere. And so the equation will be minus h square by 2m, the time independent Schrodinger equation, d2 psi by dx squared is equal to E psi. And we can write this as, just like the case of the infinite square well, d2 psi by dx squared is equal to minus k squared psi, with k is equal to root of 2me by h. Now this is what we got in the infinite square well case for the region where the V was where the potential energy was 0, and we wrote the function as a sine kx plus b cos kx. Now this is the same thing here, but for reasons that will appear clear in a few minutes, I'll write it in a slightly different format in terms of the complex variables, using of course Euler's identity, e to the power iota theta is equal to cos theta plus iota sine theta. So I'll write psi of x as a e to the power iota kx plus b e to the power minus iota kx. So this is the same thing as cos kx plus iota sin kx and so on, except a and b will be different from the a cos kx and b sin kx which we had in the infinite square well. So this is psi of x, which was the only position dependent thing, but we know generally the total wave function psi of x comma t is equal to psi of x times phi of t. And we know what phi of t is, e to the power minus e by 2m. So e to the power minus et by h. And what is et by h in this case? We know that e is equal to h square k square by 2m. So e into t by h will be h k square t by 2m. So we can write psi of x of t as a e to the power iota kx, and we will add e to the power minus et by h. So an iota k, we can take it to be common. So what is left is iota k times x minus hk by 2m times t. And similarly the other term will be b e to the power minus iota kx and then e to the power minus et by h, and again we can take minus iota k to be common and we'll be left with plus hk by 2m t. There is an iota here, by the way, minus iota et by h. And from this we can see what this looks like. We know that whenever we have a function in which we have something of the form of x plus vt or x minus vt, it represents a wave. And in this case, we do have x minus vt and x plus vt. So this is a wave traveling in the positive x direction, and this is a wave traveling in the negative x direction. So once again, instead of writing it as cos theta plus sin theta, we chose to write it in this form because we could easily see that the waves are of the form of x plus vt and x minus vt, where v is equal to hk by 2m. And in this case, k was positive, and you have two waves, one going towards the left and the other going towards the right, but we can actually combine them into a simple wave with k going from negative to positive value. So the sign of k will determine the direction of the wave as opposed to whether it's x plus vt or x minus vt. So we can write it as psi of x comma t is equal to a e to the power iota times, now we'll take kx minus hk square by 2m t, where if k, which is plus minus root of 2me by h, because now we take it to go to both positive and negative values, if k is greater than 0, the wave is traveling in the positive direction or traveling towards the right, and if k is less than 0, the wave is traveling towards the left. So instead of having two waves a e to the power iota something plus b e to the power minus iota something, we have a single wave which can travel towards the left and right depending on the sign of k, and the speed is given by hk by 2m. Right. And what does that come out to be? hk will be root of 2me by 2m, so it turns out to be root of e by 2m. So basically for a free particle, this would be the solution, a wave traveling in either the positive or negative direction with a speed root of e by 2m. But there are two problems in this which need to be resolved. The first problem is that this v is not what we are supposed to get. In kinetic energy, we have E is equal to half mv squared, which means v is equal to root of 2e by m. So if this is v quantum and this is v classical, v classical is equal to 2 times v quantum. So we are getting the wrong value of velocity. If we think of a wave traveling towards the right as a particle traveling towards the right, because we want to make this connection between particles and waves, then the speed we are getting is half of its original value. We would expect that the speed would be root of 2e by m, but it actually turns out the speed of the traveling of the wave is root of e by 2m. So there is a contradiction here and we need to resolve it, which will resolve around the end of the video. The solution, I'll just tell you right now, is that this VQ does not represent the speed of a particle. It represents the speed of the wave moving, but if a wave is supposed to represent a particle by something called a wave packet, which we'll see in a few moments, then this speed does not correspond to the speed of the particle. So the speed of the particle will indeed come out to be this thing called the group velocity root of 2e by m. But there's another problem which is more immediate and we need to take care of. This wave turns out to be not normalizable, because if you try to normalize it, integral of psi star into psi would simply give you integral of mod a squared dx minus infinity to infinity, because e to the power iota, this thing multiplied with the complex conjugate e to the power minus iota, this comes out to be basically infinity. So there are two problems with this solution, which is why we did this case after we did the infinite square well and the harmonic oscillator case. The first is the speed does not come out to be what we would expect. It comes out to be half of that value. The other, this wave function which we got as the solution, is not normalizable. Another way of saying that, we know that separable solutions in this case do not represent physically realizable states. These are the separable solutions and they do not represent physical states. Means they don't correspond to any real particle or real wave which you might have, because we know in quantum mechanics a wave has to be normalizable, because the total probability of finding it between minus infinity and infinity, or total probability of finding it all throughout space, has to be 1. And another way of saying that would be, we assume there to be a definite energy. Right, we solved this equation for a particular value of E when there was no potential energy. So another way to say that would be, there is no such thing as a free particle with a definite energy. Because that's what we did. We assumed that there was a free particle under the action of no potential at all, which had a particular energy E. We solved it, we did get a solution, but we got two problems. One was the speed wasn't what we would expect, which we'll deal with in a few moments, and also that the wave function was not normalizable, which meant that it could not represent a true particle or a true wave or a true object, because true objects have to have wave functions which are normalized, which means the integral of psi star psi all over space has to be equal to 1. So there is no such thing as a free particle with definite energy. But that does not mean that everything we've done till now is useless. We can actually use it to create something which looks more like a physically realizable object. And that is done by adding many different solutions together. So you had solutions a e to the power iota kx minus hk square by 2mt. And what you can do is, you can take many different values of k and add these together. So you can take k is equal to 1, then you can take k is equal to 2, and add it with half the amplitude. You can take k is equal to 4 and add it with 10 times the amplitude. You can basically add a number of these waves together, and if you do it properly, it will turn out to be something that is normalizable and that can represent a real physical state. But instead of now taking discrete values of k the way we took discrete values of n in the infinite square well and the harmonic oscillator case, now we'll take continuous values of k. So instead of a, what we'll have is some function phi of k, which depends on the k, and instead of summing, now we will integrate from minus infinity to infinity with d of k. And this can be a psi of x comma t. And we just add a 1 by root 2 pi for the sake of convenience, because it makes things a little bit simpler. And the moment you notice 1 by root 2 pi, some of you who've done mathematics courses would realize that we are going into the realm of Fourier series, because that is what this equation looks like. But before that, let's properly understand what this equation is. This equation is a bunch of different psi of x comma t is equal to a e to the power iota kx minus hk square by 2m t. This itself wasn't normalizable, but if you add many different values of this for different values of k, or even if you add an infinite number of them, which is why I used an integral with k going from minus infinity to infinity and a depending on k. So instead of a of k, we've just used phi of k as a function. Then this could represent a physically realizable state if it is normalized, if it can be normalized. So not always, but if you're able to add an infinite number of ways like this for different values of k, and if you can add them in such a way that the solution psi of x comma t would be able to be normalized, then you could have a physical state. But now remember, this is a physical state, but we do not have a definite energy anymore. K depends on energy. And now when we have a bunch of different values of k being added together, then we have a bunch of different values of energy. So when we talk about definite energy, we do not have a physically realizable state. But if we talk about different energies and add different waves at different energies together, then if it can be normalized, we do have a physically realizable state, which might represent a proper particle. This thing is called a wave packet, because it is not just a wave moving with a particular speed, it is a number of different waves superposed together. And a number of different waves superposed together can form something like a wave packet. For example, this might be a wave, this might be a different wave, but if you add them together, you might get something like this. And this is the whole wave packet which moves forward. And this is what looks like a particle in classical mechanics. So the wave packet is basically a collection of different waves with different wavelengths or different wave numbers, which are k, and when they are superposed together, they form something which in itself is vibrating in the transverse direction and is propagating at different speeds because k keeps changing, but this whole thing keeps propagating in the forward direction, and this whole thing is a wave packet, which is what we would see as a particle in classical mechanics. Now here let's go back to Fourier series and see what actually is the problem which we are trying to solve in quantum mechanics. So in a generic quantum mechanical problem, what we have done is we are given V as a function of x or xyz if it's 3 dimensions. In a free particle, we are just given that Vx is 0. And we are given the initial condition generally, the initial state, which would be psi of x comma 0. We saw how the initial state might be given in the infinite square well, and then we are able to calculate the value of the coefficients using Fourier's trick and calculate from psi of x comma 0, psi of x comma t, which is what we needed to calculate. And the same thing needs to be done here. So we will be given psi of x comma 0, and we already know psi of x comma t will be a wave packet of the form of 1 by root 2 pi, which is just there for convenience, so that we can apply Fourier series directly. Integral minus infinity to infinity phi of k e to the power iota times kx minus hk square by 2m t. Right. And we are given psi of x comma 0. But if we input t is equal to 0 here, decay also. What we get is psi of x comma 0 is 1 by root 2 pi integral minus infinity to infinity phi k e to the power iota kx dk, because this term becomes 0 at t is equal to 0. So this is what we are given, and from this the first step will be to calculate phi of k. After we've calculated phi of k, we can simply substitute that phi of k into this formula for different times and get psi of x comma t. So the whole question is, given psi of x comma 0, how do we calculate phi of k? And that is done by what is called Fourier's theorem. It is sometimes called Plancherel's theorem as well, who did it first, but the series is called Fourier series, so let's just take the name as Fourier's theorem. So what does Fourier's theorem suggest? It suggests that if we have a function f of k is equal to 1 by root of 2 pi integral minus infinity to infinity f of x e to the power minus iota kx dx, then what that means is, this means the new thing and the new thing means this thing. A function f of x will be equal to, this is capital F, 1 by root of 2 pi integral minus infinity to infinity f of k e to the power iota kx dx. Notice that there's a difference between the minus signs here. Here you have a minus sign, here you don't. So if we are given a function like this, f of x is equal to 1 by root 2 pi integral minus infinity to infinity f of k e to the power minus kx dx, then from that we can directly calculate f of k. That is equal to 1 by root 2 pi integral minus infinity to infinity f of x e to the power minus iota kx dx. If you want to see the proof of Fourier's theorem and a little bit more things, you can see a mathematics course in which this thing would be done in great detail. There should probably be a whole video to it. And so from this we can just directly calculate phi of k, which we needed to calculate from psi of x comma t, from psi of x comma 0 rather. And this is equal to 1 by root 2 pi integral minus infinity to infinity psi of x comma 0 e to the power minus iota kx dx. So this is it. This solves the problem. Given psi of x comma 0, you use this equation to calculate phi of k, and then you use the original equation to calculate psi of x, which was basically psi of x comma t. Once you know phi of k, this is equal to 1 by root 2 pi integral minus infinity to infinity phi of k e to the power iota kx minus hk square by 2m t dk. So this solves the problem of the free particle, but because we've done so much in this one video, I'd like to take one example to show you how all of this works out. So let's say we are given a free particle in quite a simple format, a free particle with psi of x comma 0 given to be a for x between minus a and 0 otherwise. So basically what we are given is, this is the wave function initial of the particle. It has the value a from minus a to a and is 0 everywhere else. Right. So it has a non-zero probability only of being found between minus a, and there it has the constant probability of being found everywhere. This is the initial state of the particle. We need to find out what the long-term state of the particle will be, which means given psi of x comma 0, we need to find psi of x comma t. So the first step will be to normalize the wave function. Integral of psi star psi dx should be equal to 1, which is equal to a squared into the integral from minus a to a, because everywhere else it's 0, dx, which is equal to a squared into 2a, which tells me that a is equal to 1 by root of 2a. The other step will be to find phi of k. So we know how we can find phi of k. it will be equal to 1 by root 2 pi times, and now a, which is 1 by root of 2a, integral minus a to a e to the power minus iota kx dx. And this will come out to be 1 by k root of pi a, after you put in the limits, e to the power iota ka minus e to the power minus iota ka by 2 iota, and which you simplify further will come out to be sine of ka, using again Euler's identity. This minus this by 2 iota is basically sine of ka by k times root of pi a. And from that we can get psi of x comma t. So psi of x comma t will now come out to be 1 by pi into root of 2a integral of minus infinity to infinity sine of ka by k e to the power iota times kx minus hk square by 2m t. Right? So this is how we've been able to solve the problem. We were given psi of x comma 0. First we normalized it to get the value of capital A. Then we found phi k by using Fourier's theorem. And then we just plugged it into the original value to get psi of x comma t. Now this integral is quite difficult to work out, but you don't need to do that explicitly. This itself is a good enough of a solution. Now finally, the one thing left is to go back to the first problem which we saw. That was that the velocity was not what we would suppose it to be. The formula we had was psi of x comma t is equal to 1 by root of 2 pi integral minus infinity to infinity phi of k e to the power iota kx minus hk square by 2m t dk. And this is x minus vt, so v came out to be hk by 2m. Right? And this was a problem because this came out to be root of e by 2m, but we know that v classical is equal to root of 2e by m, and this was v quantum mechanical. So the problem is this. First we'll write this in a different form, e to the power iota kx minus omega t, because this thing hk square by 2m is often referred to as omega, the angular frequency, and this is the form in which you've seen things probably. So vq is equal to hk by 2m, which is basically, since this is omega, vq is equal to omega by k. Right? Omega by k will give us the velocity. Now the problem is, this is what is called vp, or the phase velocity. So when you have, let's say, a wave packet like this will be, let's say, the total wave packet, and inside you will have waves like this. Then vp is the speed of movement of these waves. Right, the speed at which these waves moves forward is v, which is the phase velocity. But this whole packet does not move with the same velocity. This whole packet moves with the velocity vg, which is called the group velocity. And I'll not give the proof for this formula because it's not in your course, but the formula for group velocity is d omega by dk, not omega by k. So omega by k is the phase velocity, the speed of these waves, and this whole thing is a group, and this goes forward with vg, which is the group velocity, which is d omega by dk. And when you see that omega is equal to, my apology, this would be 2m. When you see omega is equal to hk square by 2m, that tells you d omega by dk, which is the group velocity, is equal to hk by m. And hk by m is indeed root of 2e by m, which gives us the value which we were trying to look for initially. So this is how this particular problem is resolved. So I'll repeat once more. We had two problems. One was the wave speed was coming out to be half of the classical speed. The way we resolved that was we realized that Vp is indeed half of the classical speed, but it does not represent the speed of the wave packet. It represents the speed of the individual waves which form the wave packet. But the packet as whole moves with a different velocity. The packet as whole moves with a group velocity whose formula is not omega by k, which is the phase velocity, but d omega by dk. When omega changes by a small amount and k changes by a small amount, d omega by dk is the group velocity, and that indeed did turn out to be equal to root of 2e by m. There was of course the other problem which we resolved early on, that the wave function was not normalizable, and you solve it by basically taking a linear superposition of an infinite number of waves by integrals, and then you are able to get something which usually can be normalizable, the way we saw in the previous question when it was a between minus a and 2a and 0 everywhere else. That was a normalizable wave. That was a wave of this form which was normalizable, so it could possibly represent a real particle. This completes the free particle, and as you can see that it had some complications which did not exist in the infinite square well or the harmonic oscillator. That's why we chose to do this case after the other two. And now we'll do two more cases which will not go into incredible detail, but we'll see how the Schrodinger equation can be solved for them, the delta function potential well and a finite square well, which will be a modification of the infinite square well. And when we do the finite square well, we'll see a concept which we've never seen in classical mechanics and is one of the fundamental differences between classical and quantum mechanics. That is the concept of tunneling, in which if you have a potential energy path like this and an object has this energy, classically it would come down from here and never be able to go over this path, but quantum mechanically it can actually tunnel and go through this path. After doing and the finite square well, we'll take a little bit of a detour towards mathematics and put all of the things we've learned in quantum mechanics till now in a proper mathematical formulation. So we've just learned things in a sort of ad hoc way, in which I told you what the Schrodinger equation was, I told you basically a little bit of what operators were and how to solve the Schrodinger equation for basic cases, but we'll go back to the beginning and study it all once again from a mathematical point of view, so that the mathematical concepts will become a little bit clearer. After that, we'll move on to what is the most important case in quantum mechanics, the thing which basically was the beginning of quantum mechanics, being able to solve the hydrogen atom. And the things which in Bohr's model, things such as L is equal to nh by 2 pi, in this case it wasn't the reduced h, nh by 2 pi, these things were taken as ad hoc assumptions in the Bohr model to make the Bohr model fit to the actual spectrum of atoms. We will actually be able to derive results like this and see how they come directly from the implementation of quantum mechanics, from the implementation of the time-independent Schrodinger equation. But for that, we'll have to learn the Schrodinger equation in 3 dimensions, which is why we'll do mathematics before we do all of that. Thank you.